Okay, let's get started. So today's class, we are going to be talking about stating the problem in terms of the importance of having an accurate problem statement. So our steps in going through to today's class, this is our menu for today's class. We're going to do a little bit of review of basic program from last week. We will then talk a little about the importance of problem statements. After that, we'll have a sample problem, some underlying math, basically a brief introduction on a couple of the problems by Rahim that we'll be doing. So he'll give a quick overview. Then we'll start to move through our three key examples. Our first example is using computers for data processing. Okay, processing experimental data, that's one application for doing batch processing. So my students would do that. Since I'm an experimentalist and a lot of people in Bingzu do experimental work, this is a key application for us for computer programming, is to be able to process the data that we get. Okay, I'm going to try to introduce some concepts for the following object problem, working through a sample problem, and then you'll also do some sample calculations. So you have to get a feel for how the calculation should be done before you can apply a computer to do it. We'll then take a break, assuming our time is okay, and we'll have to talk about another application. Another problem that's typical for computer programming is simulation. In fact, optical ray tracing. So we're going to, this is an application which is used for things like lens design in an iPhone camera, etc. So we'll start to slowly develop a simple program that we could do for helping us to design or using as an evaluator in an AI program to optimize lenses. So I'll introduce some concepts, we'll work through a sample problem, and then you'll have some time to do some sample calculations and diagrams yourself. Thirdly, we'll use a third application of computer programming is in numerical analysis. In numerical analysis, is basically solving equations that you cannot solve analytically. Like in calculus, you learn a few special cases, but generally those are only special cases. We need to use numerical analysis to solve a general case. So an example will be, how do we writing a program to find a root? So rather than using a computer program, we'll write our own computer program that finds the root the same way most of your computers will do it, whether it wants to find a square root, a cube root, a fourth root, the fifth root, the sixth root, the seventh root, an eighth root, or whatever root you feel like finding. Okay, I'll introduce some concepts. We'll work through a sample problem, and then you'll work through a few other sample problems so you get a feel for that. After that, if you have not passed milestone 1 already, you may go home. If you have not passed milestone 1, we will then go to the computer room. We should have the computer room at that time. We will have the computer room by that time, and we will give you your second try for passing milestone 1. So is there any questions about today's plan or today's menu? Okay, we're all okay, great. Okay, let's get started. So I'll first of all go to our website, and I think I've got it on the, okay, good, it's on the right one, good. Okay, so let's review some of the tools. So this is programming basic C tab. Oh, your progress on your milestones is here. So if you have passed the milestone, you will see a black square beside your name, meaning it's passed on your first try. The 1 means you passed it on your first try. If it's blank, you have not passed the milestone yet. Okay, we did not receive some. We have some milestone papers with student numbers that don't exist. So that could, if you don't know your own student number, you may have a blank. Okay, so that just basically, so who have not passed would be Steve, Brian Wen, Stanley, Amy, Fazo, Mary, and Kewen. Okay, so everyone else in the class that I have registered, as far as I know, have passed if your name is here. So you can always check your progress here on this link. Okay, so today, let's start with the review part. Okay? Last week, we did our first program. So as we're doing a program, we first of all open a file like welcome.c in an editor. It could be Notepad is okay, or Notepad++. Rahim showed you the advantage of Notepad++ because it changes words colors. When it knows you're programming in C or whatever language you're programming in. You tell what language you want to program in, and then it changes the colors of words accordingly. Okay, so why are the words different colors when we do this edit, when we use Notepad? It's very simply that the text editor recognizes words that have significance in C. For example, int is a special C word. Main, void, these words have special meaning in C. So it recognizes it. So if you spell main wrong, it won't change color. And you know, oh, I made a spelling mistake. Okay. Now, what happens if you change the extension of your file name to .text or .csv? When you're doing this sort of programming, generally the answer is you'll lose your color because it now thinks you're writing a text file or a CSV file. If you give the extension CSV, it will now start to interpret your file as a CSV file, and you may find, so the colors will be slightly different because it will be CSV, it will think it's a CSV file. And is the color of the world saved in the file? Yes or no? Steve, where are you? Steve? I don't see you, Steve. Ah, good grief. Okay, already gone. No, all right. Okay. How about Daniel? No. 50%. Oh, sorry. Would you like to try that answer again, Daniel? No. Very good, Daniel. Correct. Excellent job. Okay. Yeah. No. The color of the words is not saved in the file. There is no information in the file about what color the words are. Okay. So it's only when you, because when, so if you open it in Notepad and it's not Notepad++, there won't be any color. Okay. So that's the editor we do. After we finish editing and writing our program, we then move on to the compiler. The purpose of the compiler is to change your C functions into machine language. In other words, it changes everything into a language that the processor can understand. Now, the binary machine language code it changes it into will be different depending on what microprocessor you're using. If you're using an Apple computer, this machine language function will be very different than if you're using an Intel chip or an ARM chip or an Expressive chip. So whatever central processing chip's own language, it will change it into binary code for that chip. So that's what the compiler job is, to sort of interface between your writing of a program that you understand and write it into a language that the compiler, or in other words, your CPU of your computer can understand. Okay, that's the conversion part, that this is what it's doing. So in order to do that, we clicked on the ANSI icon first and went to open a console or a command window. We then typed the command gcc -c -wall welcome.c. The GCC means new compiler collection. Okay, it's not just for C. Okay, it does many different languages. So then we have to specify what language did I write my file in. Did I write it in C? Did I write it in Fortran? Did I write it in Go? Did I write it in C++? Did I write it in C hash? What language did I write my program in? For us in our class, we're writing in C. We're not writing in Python or anything else. So it was -C. There's another minus flag, minus capital WALL. This says, please tell me if I've made mistakes. Don't just compile it if it's wrong and not tell me. Generally, you want to do that because if you made mistakes, you want the compiler to tell you you've got mistakes. And then finally, this is the name of the file you just wrote, welcome.c. So this will create, if there are no messages, it means you've been successful. It doesn't say, yay, your program compiled. It doesn't say anything. It just gives you no error messages. So What does this statement do? Our first question, it converts a human readable text file to a machine language file. So welcome.c, we get a new file, welcome.o. Or in other words, like your ASCII gets changed into a series of ones and zeros that your computer understands. It's similar to translating, like if you want to translate from Chinese to English or Vietnamese to English or French to English, right? If I only understand English, you first have to be able to change whatever you want to tell me into English. You can't tell me in Vietnamese. Okay, what is the purpose of each item? Okay, let's have our, okay, what's the purpose of each item? Okay, what's the purpose of the minus C? Okay, I write GCC minus C minus wall welcome.c. What does the minus C tell me? Tell the say.
C.
Right. It's a C language program. Very good. Yes.
What?
All right, pass it to the next guy. What does minus WALL do?
Welcome those and right?
Okay. Welcome.o is the final output. What if I didn't put minus WALL? What would happen?
I don't know.
Okay. Very good. Good answer. Okay. If you did not put minus WALL and your code has no errors, there would be nothing happen. Everything would be exactly the same. But if your code has something strange in it, a mistake, you will not get an error message saying you've made a mistake. You need this minus WALL so you'll get messages saying, hey, I think you made a mistake. If you don't put it there, C is not going to tell you made a mistake. By default, it doesn't tell you. Okay? So once you know that program is got no mistakes, you can then compile it without the minus WALL because you know it's correct and it'll be faster. Okay, that's all. And finally, welcome.c is what?
Just welcome.
Okay, right. Okay, good. Yes. The file you wrote, the file that you wrote, your program that you wrote that you can read. Very good. All right. So if I will, so GCC says run the GCC compiler or linker. GCC means new compiler collection. Minus C, the language of the input file. C, example, if I put minus F, it would mean it was a Fortran program. Minus ANSI, I don't have that flag here. This one is an optional flag. It would check to see if I'm using the C standard. And basically, that specifically is if you want to run on an old computer. It will check to make sure, okay, this code will run on a computer from 30 years ago. No problem. Okay? If you are thinking about running on a 30-year-old computer, you probably want to add minus ANSI. If your computer's made after 1990, you probably don't need that minus ANSI flag. Okay? Minus wall, show all warning messages and possible mistakes, and then your program's name. Can I call my file iloveali.cf? Can I use this and have it and make my program run? If I use this file name, will this work with GCC? Yes or no?
Yes. No.
Very good. No, that is the correct answer. No, it will not work. The problem is not the .cf, although that's very bad style. The problem is the space here. Okay? It won't know, are you giving a bunch of extra flags? Oh, GCC minus C minus wall, I. Next flag is love. The program's name is ali.cf. It will think that and will say, what? No. So you need a combination of letters and numbers, no spaces. Ideally, this is optional, but I suggest less than 9 characters long. And ideally should be C. But because if you use .py, you will think it's a Python program, right? And And you'll get some strange messages too, right? Because there's not a Python program, you're writing a C program. So let's make sure we .c because we're writing C programs. In your Python class, write .py. Don't reverse. You're right. Okay? Good. Okay, let's move on. That's compiling. The next step is linking, which its purpose is to combine machine language functions from different files into a single machine language file or executable program. For example, you write gcc -o w.exe welcome.o. So what does this statement do? Okay, and we'll look at what the purpose of each item is. Okay, first of all, it combines and links your machine language functions with those in libraries. For example, in welcome, we had a function fprintf. You didn't write fprintf. Somebody else did. Okay? So you need to find the file that fprintf is in, which is stdio. And so you will then have to link it to that, and the program will then run on your specific program operating system CPU. So as I said, it's like translating English, French, Spanish, and Chinese to Latin or to Creole, if the computer only, okay? All right, now what does each item do in this line, okay? GCC says run the GCC compiler and linker, -o, okay? The input is not C language files. The input now is machine language files, okay? So I'm inputting a machine language file, which is a .o file. And .exe, that's the name of your final program. And these abc.o, welcome.o are the names of the machine language files you want to combine to make the executable file. All right? And finally, the last step is run. To execute the program, you can type welcome or welcome.exe. So what does this statement do? It sends a request to the operating system. Schedule my program welcome.exe as a job. The next step depends on the operating system. The operating system's responsibility. Run the program, reject running the program, send a warning message to the user. Wait until other programs end, then run the program. So after you've sent that request, you've typed welcome, it's the operating system's decision what to do. Remember when you first started to run the installation, right? Instead of immediately running my program, what did the operating system do? It said, are you sure you want to run this program? Take me back to safety. And you said, of course I want to run this program. Advanced options, I want to run the program, run the program. So the operating system was being cautious. It realized I was running a program, a C language program that it did not know about. And knowing C is a very dangerous language for hacking computers, it gave a warning message for me. Okay? This welcome.exe, it decided it wasn't worth warning you about. That it was quite a safe little program, so it didn't bother warning you. Okay. Now, here I said you can type welcome or welcome.exe. Why do I not need to type the .exe file? Because you're using MS Windows. Okay? It can identify some extensions. If you have .exe, it says it's an executable file. If it's .bat, it's a batch file. If it's .txt, it's a text file. If you put .csv, it will open with Microsoft Excel. Okay? By default. So it sort of recognizes these programs and okay. And finally, can I type welcome.exe? Of course you can. No problem. You just write the whole name. Of course you can. But you don't have to type the exe. And finally, we talked about debugging, but we did not go into it. We will go into debugging later because it's helpful. But right now, we don't have a program that's useful to debug because it's too short. Okay, so once you've compiled, you linked, debug, you just run this gdb, new debugger, and then your program's name, and then These different things allow you to display what different variables and things are in your program. We'll discuss that again later in the course, but I put it here for completeness. And if you are confused with debugging later, you can use this as a reference. And it's also on the back of your book. Okay. So that completes our review. Let's move on to the importance of problem statements. Okay, why do software projects fail? Why do software projects fail? This is from Forbes. So this is business. So that we're talking specifically about business software in business. The number one reason, not understanding the needs of the business. In other words, you start programming without clearly understanding what the person wants in their program. I could say that in another way. There is poor problem definition. You don't understand completely what the problem is the business wants to solve. They've communicated that incorrectly to you. You work on trying to solve it. A second, fourth pre-reason they list is not starting with the end customer. You write really great software that solves a problem. But when you deliver it, you find out it's not the problem, it's not the customer's problem. Okay? In other words, poor problem definition. Basically, this is again, the programmer didn't understand the problem he was supposed to be solving. Next, number 5 is similar, unclear requirements. Okay? You immediately start programming before bothering to be clear. You don't even bother to clarify what you're trying to program. You just say, oh, I got the idea. I know what I'm doing. And you start writing a program. And then without this detailed explanation, or i.e., poor problem definition, your software project fails. So those first 3 are all related to poor problem definition, not understanding the problem clearly. So that's why we're going to spend one class to understand problems. Okay? Number 8 is the number 8th reason, which we're also going to talk about, is thinking that scope can be defined up front. Thinking that scope can be defined up front. Okay, what does this mean? You understand clearly the original problem, and you solve the problem the customer brought to you. But the customer, after you deliver, the customer realizes, hey, this is solving this problem, but I've got many, many cases that don't fit my problem. And we fail to adapt the model for these new cases. For example, most early, U.S. banking and social security system. It's written in the language called COBOL. Okay? COBOL, in original COBOL, date is defined like 000115. Okay? All right, so, okay. That worked very good. Not when it was written in the 50s, the 60s, the 70s, the 80s, the 90s, 2000, 2010. But suddenly now, we are starting to have people who would be born in 1901. Their date is 01. A person born in 2001, their date is 01. You generally get Social Security number in the USA when you're 20 years old. So by around 2021, you start to have people that are, getting their new Social Security number, because the numbering, it immediately starts to think, hey, this person might be 120 years old, because the date is, and so someone like Musk will come in and just look at the program and say, hey, there's a person here 120 years old in the system. Well, no, That's because COBOL is only representing the years by 2 digits. That person is actually 21 years old, not 121 years old. So this is a case of misunderstanding old code and old coding languages. Because when people are writing COBOL in 1952, nobody think their program is still going to be running 70 years later. I mean, yeah. So you're writing, yeah. So this is a big problem both in banking and in US code and in air traffic control. It's also at the core of a lot of air traffic control. You notice that there was a plane crash in Washington between a helicopter and an airplane. Yeah, part of that reason for that crash is because they have not updated the software and transmission things. It's back, the system being used goes back to the late 1940s. Okay? 1940s. Things have changed since 1940, right? But these systems are still clunk, clunk, clunk. They were designed then, they were developed into the 50s, and they work well, but now we're 70 years later and we're still using the same system in the air. Other places don't use that. Okay, so you need to adapt, and we're going to see that in the optics example. All right, so no, we're not that time yet. We are now time for let's see, we're back to our schedule. Sorry, it's okay, it's sample problems and underlying math. A brief introduction by Rahim. Thank you, Rahim.
The following objects.
Oh, okay, we'll do both of them. We'll do your couple ones first again, then we'll come back. Okay. So we'll start by introducing the ones that are more complicated optical ray tracing, right?
Yes.
Okay, great.
So before we start, with the optics problems, let me introduce a few things. So based on my past experience, I have observed that a lot of students have problems making these diagrams. So let me introduce a few things and rules that are needed. Okay, so first of all, by the way, you can open up page 35 in your booklet, and it says optical ray tracing, and this is what we will be doing this month. Okay, just for reference. And I hope you remember all of this from your high school or wherever. We need to realize that this line passing through the center of the lens is called the optical axis, or the principal axis. Okay, so in this case, we have an object. For calculations, we would be knowing two things. That is where the object is placed and what the focal length of the convex or concave lens is. So the object and in this case has been placed at 2f in this example, so to say. And as you can see, we're taking this one single point of this arrow, and these rays of light, these are all the rays of light that are getting reflected off that point. So in this example, that says many, you can see that a few of these rays of light are passing through the convex lens. The principal one is the important one because it tells us about the three rules that we need in order to judge where the image is going to be formed. So the rules are: any line that passes through the focal length after passing through this convex lens is parallel to the optical axis. Any ray of light that is parallel to the optical axis then passes through the focal length after getting refracted from the convex lens. And the last rule is that the ray of light that passes through the center goes as it is, it does not bend. So what we have to look out for is the intersection of any of these two lines. So any of the two rules are enough. So once we get the intersection, at that point, we get to know, okay, this is where the object is supposed to be, and this is how much height it is supposed to be. So when we're drawing these, we will get a rough idea, or at least an exact idea if we're using a ruler, to where the object is going to be and how big it is going to be. So once we're done with this example, now we can, since it's a simulation, we can see what else we can do. So we can move this back and forth and see how our image is being formed. And after moving ahead of f, we can see that the image that is being formed is magnified and it's a virtual image. So now in the simulation, we can also do one more thing, that is we can change the object. Let us change it to a pencil. As you can see, this pencil is, as usual, kept back to f, and there's one more parameter that is mentioned here, that is diameter. So if we decrease it, okay, the lens has become smaller. If we increase it, it has become bigger. But one thing that you can realize is if the diameter is small, the image that is being formed is a little dull. But if it increases, the picture gets clearer and clearer. And that is because the bigger the diameter, the more amount of light is going to be passing through, therefore a clearer image. This also implies a very interesting fact that if you were to cover half the convex lens, you would still get a real image. The only thing is, since there would be less light passing through, the image form will be dull. Now we can see the example of the concave lens, and while looking at the concave lens, you will see that it's always a virtual image being formed. So we can move back and forth the object, and you can see what is happening. So that's it, easy. Okay, so I think it's inspiring to know some examples of what we're learning in our daily lives. So let us talk about the human eye. Over here you can see the eyeball and the objects that we see at the infinity. The rays being reflected from them converge through the eye lens towards the retina, and an image is formed at the back of the retina. Some of us have problems, and they can be categorized as hypermetropia or myopia. And so what happens in hypermetropia is that the image is formed beyond the retina. So this condition is called farsightedness, in which you can see far, and in order to correct this, you need a convex lens or a converging lens. Now, one of the important things to know while you're doing the calculation is that for convex lens, f is positive. In the condition for myopia, which is known as nearsightedness, in which you can see close, what happens is that the image is formed before the retina. In order to correct this, you need a concave lens, which is also called a diverging lens. And important to note that the focal length is negative in this case.
Okay, so I cannot see far away things, so therefore I have myopia. So I am using a concave lens in this case. So the simulation that we were looking out for, you can have a look at it if you scan this. You can use it on your phones. I hope you can scan it. Oh, sorry, wrong one. Yes, that's the wrong one. Wait a second. I named them wrong. Okay, it's this one. Is the link working? So when you're solving, you can refer to this, and you can really see where your image is being formed, and how much it is magnified, whether it's virtual or real. So you can do that. Okay, so the next one that we have to do is root, finding the root. Okay, so the page number is 48. Okay, you can follow along. So I will be solving how to do it, the bisection method.
Okay, so our next task is to find roots. Square root, cube root, however many roots we want to find. So one term that we come across is significant figure. What this means is that we know that the square root of 2 is how much? 1.4. So one significant figure is being able to find the first number. Second significant figure means finding the second number in the whole series of numbers that we have for the square root. This is the third significant number, fourth significant number, and so on. And now that we are here with this terminology, we can start solving. So the question that we are going to do is we want to find the square root of 3. Okay, so for that we say that square root of 3 is equal to a number, let's say a variable x. Okay, if we square both sides, then it gives us 3. The 3 to one side is equal to 0. Now we can say that this is a function of x. This is a function of x. We can define it as x squared minus 3. We can also call it that this is y is equal to f of x. And in mathematically writing it like this, we can say that this equation needs to tend to 0. That means that this equation should be closest to 0 or even equal to 0. Now that we have this equation, now we can start solving. So let us assume, so what is the highest value or the lowest value you think could be for x? So let's try with the highest one. Let us try the highest value for the number itself. So y is equal to 3, right? So y is equal to 3 is minus 3 equal to 6. Okay, now this is greater than 0, right? Now let us try the lowest value, which is 1. So therefore y is equal to 1 minus 3 is equal to minus 2. And y is less than 0 in this case. say that the value of x will lie somewhere between 1 and 3. So the value of root 3 is somewhere between 1 and 3. So since it's somewhere between 1 and 3, we can just simply take an average of both of these numbers. So 1.3 divided by 2, which is equal to 2, right? So now we calculate what is the value of y if we keep it as 2. 2.4 minus 3, which is equal to 1. And 1 is greater than 0. Since it's greater than 0, we can say, okay, root 3 is going to lie between 1 and 2. Okay, now since it's between, we take an average again, 1 plus 2 and divided by 2, which is 1.5. Okay, now putting this value of x into the equation again, 1.5 squared is 3.25 minus 3 equal to minus 3.75. And so we can see that this is less than 0. Since this is less than 0, we can say that the value lies between 0.5 to 2, right? Now remember, we are finding up to 2 significant figures. One significant figure has already been reached, that is 1. So taking number between 1.5 and 2 is equal to 1.5 plus 2 divided by 2 is equal to 1.75. And as we can see, the square root of 3, what is it? It's square root of 3, we need to know if we calculate it separately, is somewhere around 1.732, right? So we have a second significant figure. So at this point we can kind of stop, but let's still go ahead, okay, and try. So keeping the value of x as 1.75, the equation will be 1.75 squared is 3.06 something minus 3 equal to 0.06, which is greater than 0. So now we have come closer. We can say that okay, it's between 1.5, the value of this is between 1.5 and somewhere around 1.75. Now we can go ahead and solve this. The more we solve, the more significant figures we will get. And so, you know, so this is how we do the calculation. Hope it helps you. Now one very important thing that you might have observed while solving all of these three problems is that you must have observed a pattern. Now, whenever you are coding, you always look out for a pattern. Why? Because that linearizes our problem. Like, we identify a pattern that now we can automatically do things further. Like, now I know this is what I have to do. I have to find the average of the two numbers, then use it in this formula, get the value, do this again, and the more I do it, the more significant figures I get, the bigger and more accurate value I get. So, and you must have seen this similarly in the gravity problem as well, where you are dividing the distance and then the time, and you're getting the.
Okay, so before we get to the break, you can also scan this one. And on this website, you can write down the equation. So we were solving for x squared minus 3. You can write down any other equation, and you can see how the graph is being formed. And try to find out what would be the value of x. Like, what is the square root of 3 according to that equation, or square root of 2, or any other equation. Okay? Break time.
Okay, we have a 10-minute break now, guys. Okay, we're now moving to our final segment. We'll be looking at the third example, problem solving for the third example, numerical analysis, finding a root. Well, again, we'll introduce the concepts, work through a sample problem, and then your turn. So Rahim has already given you a quick overview. So we're just going to come out a second time in a more, maybe a little bit more depth, hopefully this time. Okay, so here we are, root finding. So what was my, what happened to my mouse? Oh, there we are. Okay. All right. First of all, understanding the problem. Understanding the problem. Oh, good timing. All right. Okay. We would like to write a program to calculate the root of p, where p can be any number greater than 1. Okay? I want to be able to calculate the root of any number greater than 1. And in particular, I'll start with the square root because that's simplest, where p is a positive number greater than 1. That's I've been given this job. Now I will try to write, I'll start working towards writing my program. So first of all, again, as Rahim was showing you, we start with a hand calculation to solve for x. For example, a sample calculation. Square root of p, we'll do square root of 2. Okay, Rahim did square root of 3. It could be any p value you want to play with to try to get an idea. So our solution is x. So x equals root 2. Our goal is to solve for x. From a numerical analysis point of view, when we want to do this, we now have to convert this into an x squared equals 2, and then convert that into an equation, y equals f of x equals x squared minus 2, and it should be going to 0. The closer we are to 0, the closer we are to the actual square root, because square root is an infinitely long number. So we can never say we have the square root of 2. We are close to the square root of 2. The closer this equation is to 0, the closer we are to the square root of 2. Okay, so we want to send this to 0. Okay, we can look at a graph. I can now plot x squared minus 2. And I want this to go to 0. So if I plot that, here's x. And this is, I'm plotting x squared. Okay, so this is a function of x, y. This is x, this is y, where y equals x squared minus 2. So I plot the curve, and I see it crosses y equals 0 somewhere around 1.4. It's this point that I want, if I can find where it crosses the axis, this equation crosses the axis, f of x equals x squared minus 2, where it crosses the y-axis, that's my solution, right there. So how do I start to do it? Okay, I try x equals 2, and okay, let's try x equals 2. I see, oh, it's too big. Let's try x equals 1. Oh, it's too small. Okay, let's try, so I say let's split the difference. I know that 1 is too small, 2 is too big. I'll split the difference and try 1.5. I'll try 1.5. I find y is greater than 0, so I'm on this side. So 1.5 is too big, right? So I know my answer is going to be less than 1.5, but greater than 1. So now I have this range for my solution. 1. So there's my 1 is less than it. Root 2 less than 1.5. So I split the difference again. Let's try 1.3. I don't want to worry about the extra decimal place. 1.25. Okay, 1.3 approximately. Okay, it's good enough for me. So I'll try 1.3, and I'll come on, move mouse. Okay, so 1.3 will be about here, and it's still negative. So now I know my square root is between 1.3 and 1.5. I'll try 1.4, halfway between the two, and I find it's still negative, but very close to 0. So I can say basically my root is between 1.4 and 1.5. I have two significant figures because basically it's 1, 2. I have two significant figures now because it's 1.45 or something like that. I could estimate it as 1.45. Two significant figures is 1.4 something. Anyways, I know it's less than 1.5. It's going to be 1.4 something. Okay? So I've got it to two significant figures. I have a range for the possible values of the square root of 2. And I can keep doing this and getting slowly closer and closer. So there's my first one, 2. There's where I tried x equals 1, too small. I split the difference. It's too big. I split the difference. It's too small. I split the difference. It's still too small, but I'm getting really close. Okay, so I know it's right in this little range right here. Okay, and I can read that as 1. Okay, there's our hand calculation. So let's generalize. So we've done an example. Now we have to generalize. So once we've seen how something works, we try to generalize to a general case. If we're going to write a program, it's got to be able to not just do root 2. Okay, so in other words, I'm going to write, my step is to write as y equals f of x, i.e. y equals fx minus equals x squared minus p. I need two starting points, one bigger and one smaller. xs is the small one, xb is the big one. I can know that in square root, 1 was less than square root of 2 is less than 2, so I could use xs equals 1, xb equals 2. So generally, 1 is going to be less than the square root of p is going to be less than p. So let's just use xs equals 1, xb big side equals p. Okay, it's an easy guess. It won't be wrong. Okay, and it won't take that much more time for the computer. One that's too big, one that's too small. And then I'm going to start to solve for y using iterations, again and again and again, getting narrower and narrower and narrower and narrower. So that's the idea of iterations or numerical analysis here. Okay, for solving this equation. Okay, so they would then want to generalize the solution. But at this point, please turn in your books to page, what page are we turning to? Guys, Rahim, what page? Since I seems my page numbers are different from everybody else's. 48. Okay, 48. I think now I'm looking at my original test copy, which I did the numbering of the pages wrong. Okay, so you can see example 1.1 is a example of how me calculating root 2. Please do the same thing, complete for root 6 and the square root of 6 and the cubed root of 9, because we want to generalize to do the any root. Okay, so you know how to do square root. Cube root should be very simple, right? You now know how to do cube root too, right? Same thing, or the fourth root or the fifth root, whatever root you want. Okay, so look through the first 1.1 example. Then we'll do example 1.2, 1.3, have the TA stamp. After the TA has stamped all three of your things, you have all three stamped by the TA, will do one of two things. You will, or three things. You will help somebody else, you will go home, or you will go to write the milestone number 1 again. If you did not do the first test last week, you need to pass it this week, or try to pass it this week. Okay? Once we have people doing the milestone, Rahim will, or Alec, why don't you go up, and me and Rahim will stay here. Alec will go up to 60406, assuming it's not locked, and he will watch you as you do your milestone, okay? And we'll come up a little bit later if you need to be taught how to do the first one, okay? We can do teaching, and then you can try it again next week, right? Next week, okay? All right, okay? So that's the rest of the day's class, okay? If you have questions, please ask. We'll walk around.